Okay. Let's now try to do to prove this proposition. It turns out this proposition is key to tell us the number of conjugates of H. Okay, so let me explain why this proposition tells us about the number of conjugates of a subgroup. Then we're going to go back and prove this proposition. Okay. Okay, so we have just another proposition. Let H be a subgroup of G. Then the number of conjugates of H in G is just the index of the normalizer of H in G. And our proof we let X just be the conjugates of all the set of all subgroups of G. We let G act on X by G times K is just GK G inverse. This is the group action. And then the orbits of X correspond to sets like GK G inverse, where G is an element of G. So orbits of X basically correspond to the conjugates of a given subgroup. And then the orbit stabilizer theorem, and what's it? Yeah. The stabilizer of K in X is just the elements G such that GK G inverse equals K. That's the stabilizer of a subgroup. And the orbit stabilizer theorem, okay, this is just the definition of what the normalizer of K is. And the orbit stabilizer theorem tells us that the size of the orbit is equal to the index of the stabilizer in the group. So we have the orbit stabilizer theorem tells us that the index equals the number of elements of the orbit and the size of the orbit of K is number of conjugates of K. Okay. So finding the size of the normalizer tells us how many conjugates a subgroup has. And that is what we're interested in. Okay, so that is why we are going to prove this proposition, which I'll just turn back to briefly. The proposition that we're now going to prove. Okay, So this proposition tells us about the size of the normalizer. That's what we want. That tells us about the number of conjugates of a subgroup. Okay. So, and it tells us about the size of the normalizer of a P group. Sylow P subgroups are P groups. So that is where we'll apply this proposition. Okay, so now we're going to prove this proposition by letting H act on the cosets G mod H and see what happens. Okay. So let me just briefly state what we're trying to prove. We're trying to prove that the normalizer of H is congruent. This index is congruent to this index mod P. Okay. And what we're going to do is we're going to let X be the cosets of H. And we're going to let H act on that. H times GH is just HGH. Then we get a group action and H is a P group. So we get the class equation. Okay, so by a class equation, in the case for P groups, we get that the number of elements of X is congruent to the number of elements of the center of the group action mod P. Okay, X is just the cosets of H. So the number of elements of X is just the index. Okay, so already if we look at this equation, it's like matching up with about half of this one. Okay, so far we have this half. We want to get this half, and I guess that is the more tricky part. Okay. Right. So let's in order to prove it, we have to unravel what is this Z. Okay, it's just those cosets GH such that HGH equals GH for all H. And we've already noticed that this can be written as, that's all the cosets GH subject to the condition that GH G inverse is a subset of H. This is by what we just proved. We use this property in the proof for the second Sylow theorem that all the Sylow P subgroups were conjugate to each other, and now we're using it again. Okay. Okay. And then what is this Z? How many elements? So what is this Z? Well, it's all the cosets GH subject to G being in the normalizer of H. And if we think about what that is just the left cosets of H, which live inside the normalizer of H. Because we're looking at left cosets of H, and G is coming from not the entire group G, just the normalizer of H. Okay, so the number of elements of Z is just the index of H in the normalizer. Okay, now if we plug this into the other side of the equation, we get the index of H in G is congruent to the index of H in the normalizer of H. Okay, and that is what we wanted to show. And the only thing now is to see for a P group, why does this tell us about the number of conjugates, or sorry, for a Sylow P subgroup, why does this tell us about the number of its conjugates? Okay. So now we have theorem, the Sylow third theorem. Okay. Let P be a Sylow P subgroup. Of G. Let NP be the number of conjugates of P. Then NP divides M. And 2, NP is congruent to 1 mod P. Okay, so for the proof, first of all, the number of conjugates of P well, that is just the index of the normalizer of P in G. Okay, that is true even if for any subgroup, right? To find the number of conjugates of a subgroup, you compute the index of the normalizer in the entire group and done. Okay. So it's true for this group P, this Sylow P subgroup. And now we just want to see why does that divide M? Okay, if we look at G, P to the K times M is the order of G. The order of G can be written as the index of the normalizer of P and G times the index of P in the normalizer times the number of elements of P. Why is that? Well, maybe we just need to write a few lines about that. You know, we have by Lagrange's theorem, basically, the number of elements of G is the number of the index or the number of left cosets of H in G times the number of elements of H. Okay, that's true for any subgroup H. So we apply it for the normalizer of P. So the number of elements of G is just the number of elements in the norm, like the index times the number of elements of the normalizer of P. Now do the same thing for the normalizer of P, the number of elements of the normalizer of P. That's just equal to the index of P, that normalizer, times the number of elements of P. Okay, Now plug this value into this equation, and we get this equation. Okay, and what is the number of elements of P? It's just P to the K. So P is just P to the K. So cancel out P to the K on both sides. You have M equals the index of the normalizer times the index of P in the normalizer. Okay, so this number divides M. That's exactly what that says. So this is NP, so NP divides M. That's what we wanted to say. Okay. Now, we want to see why is NP congruent to 1 mod P. We also know that the index of P and G is congruent to the index of the normalizer of P and the normalizer of G mod P. Okay, now if this index is just M, so we can replace it by the index of the normalizer, P times this. Okay. Now modulo P, what I have is an equation like A times B equals B. Okay, also I know that these two numbers are co-prime to P. Okay, let's state that. But P does not divide M, so P does not divide either of, especially it doesn't divide this, because this is a divisor of that. And what that tells us is that so what this tells us is that this is invertible mod P. Okay. Why is that? Well, maybe we could let B be this index. And we know that P does not divide B. Well, since that tells us that the GCD of P and B is 1, that means that we can solve Px plus By equals 1 for some X and Y in the integers. And now, therefore, By is congruent to 1 mod P. Okay, so now let's take this Y and we'll call this B and look at our original equation from the previous proposition. Our original equation says that this is congruent to this other thing, mod P. Okay, now I just want, this is too small, mod P. Okay, Now this is the number of conjugates of P, so I'll call that NP. This, I've just denoted this to be the number B. So I know that NP times B is congruent to B mod P. Now I can multiply both sides by Y. NP BY is congruent to BY mod P. BY is congruent to 1, so NP is congruent to 1 mod P. That's the other thing we wanted to show. We are now done the proof of Sylow's third theorem. Right. And yeah, okay, so I guess what we should do now is take another break. I'd like to, and after the break, I'd like to do another example of this kind of thing, of applying Sylow theorems. And if we have a chance, we'll talk about the next section, which is direct products. And try and, that's just kind of a quick construction. Okay, so yes, let us take a break for for 10 minutes. Well, I'll just come back on at 1:10. Okay. Okay, thanks.